All right, students, so we're going to take a look at two new algorithms here that are a little more efficient than that brute force method we looked at, but hopefully a little better as far as optimization than just the nearest neighbor algorithm that we looked at. So again, these methods may not give us the most optimal solution. So we have the repeated nearest neighbor algorithm and the sorted edges algorithm. It may not be the most optimal solution, but it's definitely more efficient, and a lot of times it will be an optimal solution. So if we think back to our previous examples, we found that the brute force method gave us this circuit, A, B, C, E, D, A, but that was a lot of work to get there, but that is definitely the most efficient solution. Then we looked at nearest neighbor, and that gave us another solution where it was this network, but that was not the optimal solution. So what we want to do is we want to improve on this, see if we can find something that's a little more optimal, but not quite as hard as doing the brute force method. So let's take a look. So the repeated nearest neighbor algorithm is just that. It's just we're going to do the nearest neighbor algorithm a bunch of times. We're going to do it from every vertex on the graph. So what we're going to do is just choose a vertex, do the nearest neighbor algorithm, which we've done before. You just select a starting point, and you go to each unvisited vertex using the smallest weights, and you do that until your circuit is complete. So here's our graph we've been looking at. And so I'm just going to start at vertex A, and the cheapest way to go, the lowest cost way for me to go is A to E. And then from here, the lowest cost path is E to D. That's 1. And then I'm just going to work my way around the diagram. I can't go back to 4. That's going to close the circuit. So I'm just going to go ahead and make my circuit like this. And I'm going to note what the total cost is for that circuit. It's 21. Next, I'm going to start at vertex B. And clearly the cheapest path for me from B is to here to E. It would be 5 or 7 going the other way. Now, I had two choices here. I could either go here for 2 or here for 2. I can't go this way because I won't be able to complete the circuit from this point. So I'm just going to try this one first, and then I'm going to go back and do this one. So here to A, and then I have to go down, around, and over. I'm going to note that one. Now I'm going to try the next one, which is this circuit. Now I have to go from vertex C. So C, again, I'm going to go to E. That's the cheapest path to go, that way. And I'm just going to work my way around. So it goes this way. Those are all the lowest cost paths from each point. I'm going to note that one. And the cost of that path is actually 19. So far, that's the lowest cost. That's the most efficient path that we can find. So we're going to try it from vertex D now. Now D, I'm going to go to E because that's 1. This one's 4. This one's 6. So I'm definitely going to go that way. And then here, again, I have two choices to make. I can either go this way or this way. So we're going to have to try it both ways. This one gives me 21. Let's look at that again. Then I'm going to come back down this way. That path actually gives me a total cost of 19. 1 plus 2 plus 7 plus 5 plus 4. Last path I have to do is from this vertex E. Now the shortest distance, or the closest, or the lowest cost, whatever you want to think about as these weights, would be 1. And then I would have to go up and around and back. So look, these 3 outcomes are all 19. There's the 3 cheapest paths. But let's take a look at them a little closer. So these 3 19s. So it turns out these are all the same path, right? They're just rewritten in different orders. So this is the last one here, which was EDA, EDA, BC, E. Let's look at this one here, CED, ABC. That's the exact same path. And so is this last one here, DEC, look, DEC, BAD. That's the same path. So they're really all just the same circuit. So we're just kind of triple counting that same circuit. And that's going to be the case a lot of times with these. When you see some that are the same value, double check, because I think they're just the same circuit rewritten. And we can write this in any order we want. Generally, we'll just start from A and write it as A, B, C, E, D, A. Let's look at one more. So this is the sorted edges algorithm. This is also known as the cheapest link algorithm. So how we work this is we basically just select the cheapest unused edge in the graph, and then we repeat step one, adding the cheapest unused edge to the circuit unless these two things are true. If you add an edge, it would create a circuit that doesn't contain all the vertices, meaning you close the graph, or you add an edge that would give a vertex with degree 3. And then we're going to repeat until the circuit containing all the vertices is formed. So let's look at an example. So what's the cheapest edge here? This one here, 1. So I'm going to go ahead and highlight that one. So that's 1. Now I'm going to look for the cheapest edge, which is this one, 2. Okay, I'm going to keep going. What's the cheapest edge here? Well, this one, 2, but that's going to create a vertex with degree 3, right? Because that would have 3 edges coming out of this vertex E. So I can't create this one. That's 2 is not going to be good. 3 is no good either, because that's going to also create that. And then this one, I can't connect 4 either, because that's going to actually close the circuit. And then I can't actually get to all the other vertices. So what's my next cheapest? This one, 5. And then the next cheapest from there would be 6, and then 7. So that's this circuit here, 5 plus 7 plus 6 plus 1, which is plus 2 is 21. Let's look at one more. Because I can have gone this way too, right? This 2. So let's take a look. So instead of going this way for 2, I'm going to go this way for 2. So 2. And then from here, the next cheapest one is that one, but I can't use this one. And I can't use this one because that's going to create a degree of 3. So I can't use that one because that's closing it. I can use this 4 here though, so that one will work. And then I can go 5 is the next one, and then 7. Hey, that's that same network we saw before, I think, where it came up with 19. So let's take a look at all of the examples we have. So brute force gave us the most efficient method, which is this one, most efficient path. Nearest neighbor did not give us the most efficient path, but then the repeated nearest neighbor and the sorted edge path gave us this same circuit. So both of those were optimal. It's not always going to end up being optimal, but in this case it was. So again, definitely a little more efficient than the brute force method, and these cases did come up with the optimal solution. Here's one that you can try on your own. So try the sorted edges algorithm on this graph. So what we're going to do is let's start from New York and figure out the most efficient circuit from New York. So pause the video and see if you can figure that out. What is the cost of that path? So here it goes. Let's take a look. I'm going to go 50, then 75, actually 50, then 70, right? That's the next cheapest, that one, that's 70. And then the next cheapest is actually 75. And then from here, the next one is 85. I can do that one. And now I'm a little stuck, right? I can't use this 120 because that's going to close the circuit. And I can't use, well, the next one there, I can't use this 100 either because that's going to close the circuit. and that's not going to work for me. Actually, that's going to create a vertex with degree 3, so that's not going to work for me. So I actually have to use this 150 here. So both of these are going to actually create degree 3 vertices, which I can't use, so I have to use that one. So that is the cheapest circuit, so go ahead and you can total those up and figure it out. So I believe that is our solution, 430. So thanks for watching, and I hope this helps.